Is that point clear? Okay. So now, after introducing big O notation, which is acting as an upper bound, now you would imagine what would be the next definition that will come through. Something that's going to act as a lower bound, correct? So the notation for lower bound is sigma. So sigma of f of n, so this is, now we are defining lower bound. Okay, so sigma of f of n is the set of all functions that satisfy the following. There exist positive constants d and capital N such that for all n greater than equal to capital N, so T of n is going to be d times f of n. So what should I put, greater than or less than, based on the fact that this is going to act as a lower bound? What do you think?
Greater.
So it's going to be greater than equal to. Okay, so this is the basis for this being the lower bound. Okay, so you saw that in the case of big O notation of f of n, the expression was T of n was less than equal to c times f of n, and this was acting as upper bound. So therefore sigma is really the reverse of big O. So what does that mean? This implies if you have T of n is big O of f of n, then you can say what? You can say f of n is sigma of T of n, because they are exactly reversed, and vice versa. Okay. So let's take an example. So 2 times n is an element of sigma of n. Why? Because we can say n an element of big O of 2 of n. Likewise, we can say n square is in sigma of n because n is in the big O of n square. You can see that we showed like how n square, so n square curve is like this, right? And n is like this. So you can see that the n square will grow faster, and therefore clearly n square is acting as an upper bound. And because n square is acting as an upper bound, therefore n is going to be acting as a lower bound for n square. So likewise, we can say n is in the sigma of 3n square plus n log n. So when I write lg, that essentially means log base 2. Okay, just this is just a notation. Okay, So this is because 3n square plus n log n is in the big O of sorry square. All right. Any questions so far? Is that clear? So if you have to show something as a sigma, you can go in the reverse direction. And if you're able to establish the upper bound, then the reverse is going to be automatically true. And this is in the big O of n square. Why? Because you just look for the highest order polynomial, and that is clearly is going to satisfy this. So therefore, sigma, it signifies that the algorithm is at least this bad. And big O signifies that the algorithm is at least this good, right? Okay, is that clear, this point? So as much as the big O cannot say how bad an algorithm is, sigma cannot say how good an algorithm is. On the other hand, big O can say it is at least this good. And likewise, sigma can say it is at least this bad. So now, if T of n is within the big O of f of n and sigma of g of n, then clearly Tn is sandwiched between, so we can see that Tn is sandwiched between c times f of n and d times g of n. And when f of n is equal to g of n, then we can say that t of n is equal to this. This is um, the theta, big theta, right? So this big theta is the order of, this is the same f of n or g of n is now acting as a bound from above as well as below. And therefore, this is the most basic sort of relationship we wanted to establish. So if you have to say formally, so this is the order. So this big sigma is the measure of the time complexity of an algorithm. So this is acting as the, um, we can say another way of saying of the order of. So more formally, we can establish big theta of f of n is the set of all functions t of n that are in both O of big O of f of n and sigma of f of n. Okay. So how can you have now have matching upper and lower bounds? So basically, how you are able to do, you pick different constant values, different values for C and D. So if you want to conceptually see it, it basically would look like this. All right. So suppose we are plotting. So this is where n is going. And suppose your t of n is going some arbitrary function. So this is your t of n. Okay. Now, so suppose the c times f of n, so when you multiply with a constant, so let's say your f of n that you're choosing here is just n. Okay. So if you're choosing f of n as n, okay, so this n is something like this, right? So this is your n. And this is your, sorry, this. This is your d times f of n. And this one is c times f of n. So what do we see here? There are two values. So here, this is the value, let's say n1, and then so for n greater than n1, you're finding, oh, sorry, where did I draw this? For n greater than this color, sorry. For n greater than some value of n, n1, beyond this point, the c times f of n is always above this t of n, right? Because t of n is this one, right? It's always above. And likewise, d of f of n, d of f of n, beyond the value 0, right? It is always below t of n. So once you have done that, then what you have proved here? You have proved here that your t of n is less than equal to c times f of n, and it is greater than equal to d times f of n, right? So this is holding true for n greater than n1, greater than equal to n1. And therefore, we can see that we can conclude here. Therefore, t of n can be said to be equal to order of, sorry, big theta of f of n. And what is f of n that we have chosen here? F of n is chosen to be n. So we can say this is big theta of n. So you can see this Tn can be really arbitrary, but we are able to map it to some well-known f of n, which we can reason about the behavior of an algorithm. I hope this is clear. What is the basic approach to come up with a bounding function for a given timing function. Any question?
Yes, sorry, could you
Yeah.
just explain the last equivalence between theta fn and theta n? The very last line you wrote.
This one?
Mm-hmm.
As I said, here you have chosen f of n to be n, right? Right? And then you chose a constant d such that the d times f of n is going always below this t of n. And you have chosen another constant. That's why the key thing is to choose different values for c and d, right? Two different constant values. When you choose c to be another constant value, then it is going above beyond this value of n equal to n1, right? So therefore, this d times f of n is acting as a lower bound, and c times f of n is acting as an upper bound.
Mm-hmm.
So therefore, the same f of n is becoming like a nice bounding factor for t of n. And because we have chosen f of n to be n, so therefore we are saying that t of n is a big theta of n, right? Because this just directly follows from this definition that big theta of f of n is the set of all functions t of n that are in both this big O of f of n and big sigma of f of n, right? This is the upper bound and this is the lower bound. Is that clear?
Yes, thank you.
Okay, very good. So therefore, okay,
I
go
have a
ahead.
question. Won't big theta always be equal to some f of n? Because like I can't think of any function that when multiplied by two different constants won't be bounded in some way or another. Like you can always pick some f of n that will be equal to big theta.
Well, if you are choosing, let's say, n, right? Suppose your t of n is n, right? Correct? And if you're choosing, let's say, f of n as equal to n square, this can never act as a lower bound for n. Because n is going like this, right? And n square is a parabola, right? It's going like this. So this, under no constant factor, you can say that it can act as a lower bound. So when the order of the polynomial itself has changed, so this always carries this relationship. T of n is going to be big O of n square. It cannot be, you cannot write, let's say, n square as a sigma of n. Sorry, I meant to write this. This would be totally wrong. Because you cannot have a constant multiplier, doesn't matter what constant multiplier you choose, to make it as a lower bound.
Okay, yeah, that makes sense. I guess I'm just asking, like, I guess more of an existence question. So there will always exist some f of n that satisfies.
Yeah. You can come up with, as I said, big O can be very relaxed, like even when your Tn is n, you can choose f of n as n to the power 5. You're still correct. You understand? You can choose whatever,
Yeah, makes sense.
right? Okay. So the point that we establish is that if f of n is in big theta of g of n, then we can say g of n is in the big theta of f of n, right? So if n cube is big theta of 3n cube, let's say minus 3n cube minus n square, right? Then we can say 3n cube minus n square is in big theta of n cube. So once you have reached this big theta notation, it can go in either direction because it is acting as both lower bound and upper bound. So likewise, if you are having n cube, which is not an element of big theta of n, you can see why it is true, right? Why n cube is not big theta of n, because you cannot show, just like I explained, you cannot show n to be an upper bound for n cube. That just cannot be possible. So therefore n cube is not an element of big theta of n. And likewise, it goes in the reverse direction as well. N is not an element of big theta of n cube. So they are kind of duals of each other, you can think of. Okay. So therefore, previously we saw how n as a big O of n to the power, let's say 8, right? One can easily write this, right? And then we said that that does not tell us that the algorithm is slow, right? You cannot conclude this. And so theta, on the other hand, so now we have reached the big theta. So big theta does not carry this problem. So this cannot be misleading because you're putting the bound from both above and below, because n is not an element of big theta of n to the power 8. So this is the key point. And therefore, when I was showing the whole table, if you remember, when I was showing the table, I made them as big theta, but at that time I did not define it, but now you can see why I put in that table big theta. Okay, so if that is clear, let's do one practical exercise. Not one practical exercise, but lay down some practical rules how you're going to actually calculate the complexity given an algorithm.